Hi everyone. In the past few lectures, we started off our discussion on the transient analysis of integrators and differentiators. Mainly, we were looking at ideal integrators and ideal differentiators. So, in the last two lectures, we spoke a lot about the step response of inverting RC integrators and inverting RL integrators. So, I thought to complete the discussion, we'll finish off the discussion by doing the transient analysis, mainly by doing a step response analysis for a non-inverting integrator. Shown in the circuit is a non-inverting RC integrator. The transient event occurs at t equal to 0 seconds. It's given that the resistance value is 1 kilo ohm, the integrating time constant is 1 millisecond, and the op amp is assumed to be ideal with a saturation limit. The output saturation limit is plus minus 15 volts. And it's also given the initial condition of the capacitor before the step input occurs, before the step event happens, is given to be Vc0 minus, and we have to analyze the circuit for two cases, when Vc0 minus is 0 volts and Vc0 minus is 5 volts. Okay, I'll do the analysis for a general Vc of 0 minus. I'll derive expressions assuming the initial voltage is Vc0 minus, and we can just finally substitute the values and get the exact current and voltage values. What you're supposed to find is the output voltage, the inverting terminal voltage, which happens to be the virtual node in this circuit. Okay, it's supposed to virtually track the non-inverting terminal. So that's the node Vx of t, and the current flowing through the capacitor Ic of t. Okay, so now let's start the analysis. So first we have to understand how the circuit behaves for t less than 0, or what is the behavior of the circuit at t equal to 0 minus. That is, the circuit has reached a steady state and it's about to receive a step input. Okay, so that's the time point which we are interested in. So the step has not arrived yet, so I can treat the non-inverting terminal to be at 0 volts. Since the circuit has been in a steady state for a long time, the capacitor will act like an open circuit. There is no current flowing through that. So IC of 0 minus will be 0. There is no current flowing through that. And it will have a voltage drop of value Vc0 minus. Since there is no current flowing through the cap, and since the op amp's input also draws no current, the current through the resistor is also 0. So therefore its voltage is also 0. So V minus or Vx of 0 minus is also 0. Now, if you guys recall from our previous discussions, I said whenever we are analyzing integrators or integrator circuits, whether it's RL integrator or RC integrator, one thing to keep in mind is that both these ideal integrator and ideal differentiator circuits do not have negative DC feedback. Okay, so in the steady state, DC feedback is like a steady state feedback. In the steady state, capacitor acts like an open circuit, so even if you apply a change on the output voltage, it will not get reflected at the negative input terminal, which means there is no feedback, right? So if there is no feedback, then we said the differential input happens to be 0 in this case. Then we said if you assume the op amp to be ideal, the output can take any value between minus 15 to plus 15. And you have to know what the initial voltage across the capacitor is to precisely say what the output voltage is. So therefore, if you assume the initial voltage across the capacitor as Vc0 minus, then the output voltage V of 0 minus is simply equal to Vc0 minus. Now we know all the three node voltages. So Vx of 0 minus is 0. The current, we know the two node voltages, that is V0 of 0 minus is Vc of 0 minus, and the current flowing through the capacitor is also 0, is 0. Okay, now we'll analyze the case when the step arrives at t equal to 0. When the step arrives, it's a sudden transient event to the circuit. Okay, there is a sudden, anytime a sudden input is applied to an op amp circuit, you should expect some sudden changes in the circuit. Okay, the moment a capacitor detects a sudden changes in the circuit, anywhere in the circuit, it's going to act like the voltage across the capacitor cannot change instantaneously, which means it's going to act like a fixed DC voltage source. If the initial voltage stored across the capacitor is 0, it will act like a short circuit. Okay, but because we are assuming the initial voltage to be Vc0 minus, it will act like a voltage source, fixed voltage source of value Vc0 minus. Now if you see, suddenly when the transient event happens, negative feedback, the circuit tends to have negative feedback. Okay, there is a DC negative feedback, right? If you just connect, for example, if I ask you to analyze a circuit like this, if you just put a DC voltage source of some value Vc of 0 minus, and if I apply an input, say Vi at this point, your output voltage will simply be equal to Vi plus Vc0 minus. Why is that? There is a perfect DC feedback in the circuit, because if you see, the small signal impedance of this of this ideal voltage source is 0. So when I'm doing a small signal analysis, I can just assume it to be almost a short circuit. Okay, so which means, what does it mean? What does this, if I say that it's short circuit, it simply means that if I change this node voltage by delta V, this node voltage will also change by delta V. So the feedback factor becomes equal to 1. Okay, this is for small signal feedback. So when the moment you assume that there is negative feedback, then you know that V minus will track V plus. Okay, so if V minus tracks V plus, this node voltage will come to Vi, and the output node voltage will simply be equal to Vi plus Vc of 0 minus. So that's what happens here. The instant your input signal becomes 10 volts, this node will also come to exactly 10 volts. Okay, and output will also come to exactly 10 volts. 10 volts, sorry, it will come to 10 volts plus Vc0 minus. And if you see, the voltage across the capacitor is fixed. That stays put at Vc0 minus. Okay, both these nodes increasing to 10 volts, this node increasing to 10 volt and this node increasing to 10 volt, simply follows from the fact that the capacitor voltage cannot change instantaneously, and there is a DC negative feedback in the around the op amp in the circuit. If you include these two factors, then you can arrive at this conclusion. I have already derived this. We solved a similar problem previously, so I don't think there is much confusion here. If you do have any confusion, just write in the comments and I'll answer it. So this node voltage will immediately jump to 10 volts, and this will come to 10 plus Vc of 0 volts. If the voltage is 0, then output will also come to, if the initial voltage across the cap is 0, then this node will also come to exactly 10 volts. Okay, so now we know the output node voltage at the exact transient event, which is the exact event when step input happens. So at t equal to 0 plus, your V naught of 0 plus is going to be Vc of 0 plus plus 10, and since Vc of 0 plus is Vc of 0 minus, the capacitor voltage has not changed instantaneously, it will be Vc of 0 minus plus 10. So your output voltage started off at Vc 0 minus, and then it will jump by 10 volts. And if you plot Vx, the node voltage Vx, that was initially 0 volts. If you plot it, it was initially 0 volts to begin with, then suddenly it jumped by 10 volts when the step input arrived. Okay, now if I ask you what is IC of 0 plus, what is the current flowing through the capacitor at 0 plus, that is simply equal to the current flowing through the resistor at 0 plus. That is simply Vx of 0 plus divided by R. If you know the voltage at the inverting terminal divided by R, you get the current. So this will simply be 10 by R. In this case, it's since R is 1 kilo ohm, it will be 10 milliamperes. See, the current through a capacitor can change instantaneously, but the voltage cannot. So the current in the capacitor will suddenly jump to 10 milliamperes. It was at 0 initially. At t equal to 0 plus, it will jump to 10 milliamperes. So if you guys have been noticing something as we are analyzing the circuits, if you notice a very interesting fact between differentiators and integrators, it is this. For integrators, there is a transient negative feedback. When there is a sudden change in the input, the integrator circuits tend to have a proper DC feedback. But there is no DC feedback in the steady state. The opposite holds true for differentiators. When there is a sudden step input or a transient event, there is no DC feedback. Okay? DC feedback happens only in the steady state. I'll solve more problems and this point will become more clearer. Okay. Now that we know what the voltage is at t equal to 0 plus, we'll now find out what happens for t greater than 0 plus. Now I just said at t equal to 0 plus, the circuit has DC negative feedback. The moment there is negative feedback, then we can apply our rules of negative feedback and simply analyze the circuit in a straightforward way. This is a non-inverting integrator. The output voltage of a non-inverting integrator V naught of t is simply Vi of t plus integral 1 by RC, which is 1 by tau Vi of t dt. Okay, so here the Vi of t is the input signal, that is 10 volts now at 0 plus. I'm trying to find out what happens for t greater than, see, remember this equation is valid only for t greater than 0 plus. Before that, this equation was not valid. The op amp was just an open loop. The instant step input is applied, the op amp now comes into negative feedback, and now then we can apply this result, right? It's just an inverting integrator. You can derive the exact expressions. I've already solved this problem, so I'm not writing that expression. In Laplacian domain, you can write it as V naught of s as Vi of s plus Vi of s by SRC. Okay, so that's what I've written this in time domain. So now if you see, the input signal is after t equal to 0 plus is 10 plus this is constant 10, so it will be 10 by tau times t. You have to, mind you, this expression, whenever you are integrating the voltage, you should also take care of the initial conditions. You should also add the initial voltage, so that will be V naught of 0 minus. I should add this. Okay, or you can, if you don't want to do that, you can directly see the voltage at the output at t equal to 0 plus is what? 10 plus Vc of 0 minus. It is 10 plus Vc of 0 minus. Now any current that's going to flow through the capacitor, through the capacitor will slowly increase its voltage, increase the capacitor's voltage. So that is captured in the integral term. 1 by RC integral 10 dt captures that term. So now if you have to analyze this circuit, now if you have to plot the output voltages, the output, because a constant current is flowing through the capacitor voltage will just ramp up. So that's what this term 10 t by tau shows. So the output voltage will start off at 10 plus Vc of 0 and it will keep ramping up till it reaches 15 volts. It will keep on ramping up till it reaches 15 volts. So for example, let's assume Vc of 0 minus is 0. So the output voltage starts at 10 volts and starts increasing linearly with a slope of 10 by RC. Okay, that slope is determined by this input step voltage. So it will be 10 upon RC. I have written this expression 10 by tau, so which is 10 volts in 1 millisecond. So if I assume 0 initial condition on the cap, the output voltage starts off at 10 and increases with a slope of 10 volts in a millisecond. So therefore in half a millisecond, in t equals tau by 2, it will reach 15 volts. Right? It's already at 10 volts. It just has to reach 5 more volts to reach 15. And if it's increasing with a slope of 10 volts per millisecond, within half a millisecond, so 10 volt per millisecond times half a milli will be 5 volts. It will reach 15 volts. So the capacitor current, if you see the capacitor current, that is remaining constant. Why is the capacitor current constant? Because the current flowing through the capacitor is exactly equal to current flowing through the resistor. And the voltage across the resistor is fixed. That is 10 by R. So which is 10 milliampere. R is 1 kilo ohm, so it's 10 milliampere. So current flowing through the capacitor was initially 0. There was a sudden step change and its value remains at 10 milliamperes for this entire duration as the output is charging up. And what about Vx of t? Vx of t, because there is negative feedback present, the op amp is not going to let it change. So Vx of t will remain constant at 10. It will stay constant at 10, initially it was at 0. The moment the step input was applied, it reached 10 volts, and it will stay at 10 volts till the output reaches 15 volts. Okay, so this is your capacitor current, and this is your inverting terminal voltage Vx of t. The moment your output reaches 15 volts, the output is saturated. The output voltage can no longer increase. Even if you are pushing additional current through the capacitor, the output no longer changes. So the change delta V naught is going to be 0 after t equals tau by 2. In this example, I am assuming tau by 2 because I have assumed Vc of 0 minus is 0. Okay, if you assume initial charge is 0, then the time it takes to reach the peak value is 15 volts. So therefore, the time it takes to reach the peak value is just half a millisecond. Okay, so which is half the time constant. So once you reach half a time constant, the output voltage has reached 15, and if you increase the time as you slightly increase the time, any extra current flowing through the cap will not change the output. Therefore, I can say delta V naught, the change in the output is 0, which means the loop gain of this circuit, of this feedback circuit, becomes 0. The moment loop gain becomes 0, there is no negative feedback. So now I can replace this op amp. I can just forget this op amp because there is no negative feedback. I can forget this op amp and replace it as a fixed voltage source of 15 volts. That's what I've shown here. Now mind you, capacitor alone, the capacitor alone has now, initially it was starting off at 0 volts because we have assumed Vc of 0 minus 0. It starts off at 0 volts and slowly it accumulates a voltage of 5 volts. Right? At the end of tau by 2 seconds, the output is at 15 volts and Vx is at 10 volts. So the voltage across the cap is 5 volts. Okay, it has increased. It was 0 initially and it increases linearly till 5 volts at t equal to tau by 2. So that's what I've shown here. The voltage across the cap is 5 volts, Vx is 10 volts, and now the circuit reduces to a first order RC circuit because now op amp is no longer in the place. It's just going to act like a DC voltage source. Now we can apply our rules of first order charging and discharging. You're supposed to find Vx. It starts off at 10 volts. Remember, in the steady state, for a long time, if you leave the circuit on its own for a long time, the capacitor should eventually act like a short circuit, which means the capacitor should eventually act like an open circuit, which means the current flowing through the circuit is 0. Therefore, Vx has to come to 0. The voltage drop across the resistor will be 0. So Vx will come to 0. So Vx at t equal to tau by 2 is at, initially it jumped to 10 volts. At t equal to tau by 2, it was at 10 volts. From then onwards, it will decay down to 0. So this node voltage Vx will decay down to 0. The capacitor voltage, it was at 5 volts in the steady state. In the steady state, when there is Vx becomes 0, the entire 15 volts will drop across the cap. So the cap's voltage will start increasing. It will accumulate more and more charge. That will be a first order charging with the time constant tau given by RC, and the steady state value it will reach is 15 volts. So I'm directly drawing this because it's just in the last lecture I told you guys how to draw this. So it's a first order system. You know the initial value, you know the final value, you can draw the graph. Okay, so that's why I'm just drawing it. Initially it's 5 volts, finally it reaches 15 volts. So it's going to be a first order charging and with a time constant of RC, which is 1 millisecond. Okay, so we can assume if it starts off at tau by 2, in half a millisecond it reaches 5 volts, then maybe if you take 5 time constants, which will be another 5 milliseconds, it will more or less reach 15 volts. So I have shown Vx here. Vx starts off at 10 volts, it decays down, eventually goes to 0. And the current flowing through the capacitor, if you monitor the current flowing through the capacitor, is simply Vx by R. Right? You know the voltage across the resistor is R. The voltage across the resistor is Vx, and therefore the current is simply Vx by R. So current will also follow the same pattern. It was 10 milliamperes after the switching event. So this is the point where switching event happened. This is t equal to 0. It jumped to 10 milliamperes, and after t equal to tau by 2, it will decay down to 0. Okay, eventually the steady state capacitor current will come to 0. Output voltage will always stay at 15 volts. After t equal to tau by 2 seconds, output voltage will always stay at 15. Okay, so your V naught of t for t greater than tau by 2 seconds will be at 15. And this is, for your output to stay at 15, the differential input to the integrator, to the op-amp circuit should always be, the differential input should always be greater than 0. And that you can quickly verify is always ensured, because if you look at the op-amp here, at the positive terminal the voltage is at 10 volts. At the negative terminal the voltage is going to be 10 e power minus of t upon tau, right? I'm not worried about the time shift here. This decaying of this voltage starts after tau by 2 seconds. So if you see, in the steady state this node voltage goes to 0 and this V plus stays at 10. So therefore steady state Vd will be at 10 volts. So therefore it's always greater than 0, and it will steady state, it will be at 10 volts. So output will stay put at 15 volts. There is nothing to disturb that state. Okay, so output will stay at 15. That completes this problem. So in case if I tell you your Vc of 0 is 5 volts, to begin with, if I'm already saying that Vc of 0 is 5 volts, what do you think will happen to this circuit? So let me, if I say that, I'll analyze this circuit here. If Vc of 0 plus is 5 volts to begin with, then how will the waveforms look like? So this is, the capacitor is initially charged to 5 volts. So initially before the step input arrived, output, this will be at 0, this node will also be at 0. So the output voltage will start off at 5 volts. The instant step input is arrives, okay, at t equal to 0, both these nodes, there is DC negative feedback, this node will go to 10, this node will go to 10, and the output will jump to 15 volts. Okay, the instant step input is applied, Vc of 0, V naught of 0 plus will become 10 plus 5, that is 15 volts. Okay, so at this point itself it has reached the saturation limit. Now any increase in current, if now there is a current set in the resistor which starts flowing through the capacitor, the output will not change, it will stay at 15 volts. So output voltage will start at 5, jump to 15 and stay put there. What about the node voltage at Vx? The node voltage at Vx initially was at 0, it jumped to 10 volts, and immediately after this event, your circuit will no longer be in negative feedback for t greater than 0 plus. See, you didn't need any extra time constant to charge the output node to 15. So previously when you started off at 0, you have to spend some time to charge it, right? The circuit was jumping to 10 volts and then it went to 15 volts and all that. But now that's no longer needed. Circuit is already reached 15 volts. So from this point onwards, the output voltage will just act like a DC source. It will simply act like a DC voltage source of 15 volts. And capacitor is already charged to 5 volts. And you have a resistor connected with a voltage of 10 volts across it. The same rules apply, and you can easily plot what will be the output voltage will stay put at 15. Vx, if you see this plot here, Vx suddenly jumped to 10 volts and then it will quickly decay down to 0. And the current flowing through the capacitor will also be the same. It will suddenly jump to 10 milliamperes at t equal to 0, and then it will decay down from then onwards. Right? It's a first order circuit, so I'm just directly drawing these graphs. First order circuit, cap will act like an open circuit in steady state, so current has to come to 0. And the initial peak current flowing in the circuit is 10 by R, which is 10 milliamperes. Okay, so that's how the circuit is going to behave when you assume Vc of 0 minus is 5 volts. So in the next lecture, we'll talk about RL based integrators.